Good morning, dear students. So far we have been discussing the characteristics, the general characteristics of alkali metals, isn't it? So we had discussed the electronic configuration, then atomic and ionic radii, and also the ionization enthalpy, isn't it? Along with the oxidation state. So next is the electropositive character of this alkali metals. Electropositive character of alkali metals. Then see here this electropositive character. See the alkali metals means the elements are lithium, sodium, potassium, rubidium, cesium and francium. Francium is a radioactive element. So here this electropositive character means these metals, they have got a strong tendency to lose the valence electrons, isn't it? The alkali metals, they have a strong tendency to lose the valence electrons, and this strong tendency to lose the valence electrons, that is called as the electropositive character. Okay, lithium, what is the atomic number? Atomic number 3, isn't it? So our electronic arrangement, it will be like this 2 1, isn't it? So it can lose this one valence electron for attaining a stable configuration, isn't it? NS2 is a stable configuration. So this lithium can lose this one valence electron in order to attain a stable configuration. Therefore, it will be losing this valence electron readily, and therefore it acquires an electropositive character. Okay. So the tendency of an element to lose the valence electron readily, that is called as the electropositive character. And also, while discussing the electropositive character of this alkali metals or group 1 metals, it is seen that the see down the group, the ionization energy, it is decreasing, isn't it? Ionization energy decreases down the group, and as a result, see, as ionization energy decreases down the group, that means the tendency for losing the electrons down the group also increases, isn't it? The tendency for losing the electron, that is down the group, the ionization energy decreases. That means as size increases, isn't it? Down the group, the size increases, and as size increases, what happens? The valence electrons will be loosely held between the nucleus, isn't it? The valence electrons will be far from the nucleus, and so the nuclear force of attraction will be lesser while the size is bigger, isn't it? While the size is becoming bigger, the force of attraction between the valence electrons as well as the nucleus will be lesser. That means it is the valence electrons, they are loosely held in the valence shell. So what happens? It can be easily removed, and as a result, so for removing an electron, it requires ionization energy. So here it requires less energy for the removal of this valence electrons for atom with bigger size or with an element with bigger size. Therefore, ionization energy decreases, isn't it? For bigger size element, ionization energy will be lesser, and as ionization energy as the ionization energy decreases, what happens? Down the group, ionization energy decreases, and as a result, the tendency for losing the electrons also increases down the group. Therefore, we can say that electropositive character also increases down the group. Okay, electropositive character increases down the group. Electropositive character increases down the group. Okay, so the electropositive character means it is the tendency for losing the electrons. See, down the group, ionization energy decreases, and as a result, electropositive character increases down the group. Then the next point, that is the 6th characteristic feature, that is the metallic character. This metallic character, it is also somewhat related to this electropositive nature. Okay, metallic character means it is also the tendency of losing the valence electrons. Okay, metallic character, it means it is the tendency for losing the valence electrons. And also down the group, we had seen what happens? Ionization energy decreases down the group. Down the group, ionization energy decreases, and as a result, this group 1 elements, they have got a strong tendency to lose the electrons down the group, isn't it? They have got a strong tendency to lose electrons down the group. Strong tendency to lose electrons down the group, and as also see, they have got a strong tendency to lose electrons means the metallic character increases down the group, isn't it? Metallic character increases down the group. So this metallic character, it is measured by the tendency for losing the electrons down the group. The valence electrons will be easily removed. So we can say that the metallic character increases down the group. So that is regarding the metallic character. So both are somewhat related, isn't it? Electropositive nature as well as metallic character. Electropositive nature increases down the group. Metallic character also increases down the group. Then the next point, the seventh characteristic feature, that is the formation of univalent positive ions. Formation of univalent positive ions. See here, the elements are lithium, alkali metals are lithium, sodium, potassium, rubidium and cesium. Cesium is the element with bigger size and lithium is the smallest element, isn't it? So here down the group, what happens? Ionization energy decreases, and also what happens is that, see, for lithium it has got a very small size, isn't it? Then down the group the size increases, that means the number of shells increases and the cesium is the biggest one. And also these alkali metals, they have got a strong tendency to lose one electron, isn't it? Lithium, it has got atomic number 3, then the electronic configuration, it is 2 1. Sodium, atomic number 11, isn't it? So the electronic configuration is 281. So in all these cases, it is easy to remove the valence electron, isn't it, to attain the stable octet configuration. See here, by sodium, by removal of one electron, what happens? The electronic configuration becomes 2 8, isn't it? Since it loses one electron, sodium, it becomes Na plus, and also for Na plus, the electronic configuration, it becomes 2 8, isn't it? So here these elements, these alkali metals, they have got a strong tendency to lose the valence shell electron, that is lose the one electron present in the valence shell. Since it is losing one electron, it will be having a positive charge. Okay, if it is losing 2 electron, it will be having a di positive, or it will be di positive ion, isn't it? Since it is losing 1 electron, it will be having a positive charge. And that means these elements, they have got, they are univalent positive ions. And also, normally these compounds, these alkali metals, they form ionic solids. They form ionic solids. For example, sodium chloride. Sodium, it will be donating 1 electron to form the configuration 2 8 Na plus, and Cl, it will be gaining 1 electron to form 2 8 8, isn't it? Cl, by gaining 1 electron, it becomes Cl minus, and the configuration becomes 2 8 8. For chlorine, the configuration is 2 8 7, isn't it? So it will be accepting 1 electron from sodium atom, and therefore it becomes Cl minus to form 2 8 8. And hence these alkali metals, they have a strong tendency to form ionic solids. So that is one important feature. So normally we can say that these alkali metals, they are univalent, that is one point. And the second point is that they can form ionic solids. They can form ionic solids. Okay, so this is the seventh property, formation of univalent positive ions. Then the eighth property, that is regarding the hydration of ions. Hydration of ions. See, normally these alkali metals, hydration means it is the addition of water, isn't it? but it can form water of crystallization. That means it can form .H2O. So here this alkali metals, they are readily hydrated. Alkali metals are easily hydrated. The one reason is that it has got a smaller size, isn't it? So that is why it can easily hydrated. So we can say that the smaller the size of the ion, what happens? The greater is the extent of hydration. Greater is the extent of hydration. Smaller the size of the ion, greater is the extent of hydration. And also see this regarding the order of hydration: lithium, sodium, potassium, rubidium, cesium, isn't it? So down the group, the atomic size increases. So here lithium has got the smallest size, while cesium has got the biggest size, isn't it? So the ion which has got smaller size, it will be easily hydrated. So lithium can be easily hydrated while comparing with that of sodium. So Li plus will be having greater hydration than sodium. Then after that, after sodium, then comes potassium, lithium, sodium, potassium, then comes rubidium, then comes cesium. Okay, so this is the order of hydration. Lithium is the easily hydrated species. Okay, lithium is the easily hydrated species. Lithium ion is heavily hydrated. Lithium ion is heavily hydrated because of the smallest size. And cesium is the least hydrated. Cesium is the least hydrated since it has got the biggest size. Okay. So that is regarding the hydration of ions. Then the ninth property, that is the reducing properties. Reducing properties and the electrode potential. Reducing properties and the electrode potential. Reducing properties and electrode potential. So first of all, you have to know what is oxidation and what is reduction. See, oxidation, it is a process. Oxidation means it is a process of losing of electrons, isn't it? And the just opposite is the case of reduction. Reduction means it is the gain of electrons. Oxidation is loss of electrons and reduction is gain of electrons. Otherwise, we can say oxidation means it is the addition of oxygen or it is the removal of hydrogen, isn't it? Addition of oxygen or removal of hydrogen. Similarly, reduction, we can write it as it is the process of gaining of electrons, or the second definition for reduction is that it is the addition of hydrogen. Addition of hydrogen, and the third one, or it can be the removal of oxygen. So these are the three definitions for oxidation as well as reduction, isn't it? And also, you know, a reaction in which both oxidation and reduction reaction takes place simultaneously, it is called as a redox reaction, isn't it? Redox reaction is a reaction in which both oxidation and reduction process takes place simultaneously. So here oxidation means it is the loss of electrons, or it is the addition of oxygen, or it can be the removal of hydrogen. While reduction, it is the gain of electrons or addition of oxygen or addition of hydrogen or removal of oxygen. Okay. Then we have to see what is an oxidizing agent. Oxidizing agent as well as a reducing agent. Oxidizing agent means a substance which can accept electrons. A substance which can accept electrons, it is called as an oxidizing agent, while reducing agent means it is a substance which can lose electrons. Okay, oxidizing agent means it is a substance which can accept electrons, while reducing agent is a substance which can lose electrons readily. And also see here in the case of alkali metals, we have been discussing the case of alkali metals, and in the case of alkali metals, what happens is that alkali metals, it has got a low ionization energy down the group, isn't it? Alkali metals has got a low ionization energy down the group, and as a result we can say that low ionization energy means it can lose electrons, isn't it? It can lose electrons readily. It can lose electrons readily, and therefore we can say that these alkali metals, they are good reducing agents, isn't it? They are good reducing agents. See here, see, reducing agent means those substances which can lose electrons, they are reducing agent. Here these alkali metals, they can lose electrons readily, hence they are good reducing agent. Okay. And also see the trend, we can see the trend of this reducing property. See what is the nature of ionization energy? Ionization energy, it decreases, isn't it? Moving down from lithium to cesium, isn't it? While moving down the group from lithium to cesium, what happens? Ionization energy decreases, and therefore we can say that the reducing properties increases down the group. Reducing property increases down the group. Reducing property increases down the group. Okay. Then the next one, that is the standard oxidation potential. Standard oxidation potential. See, standard oxidation potential means this is the tendency. See here, for alkali metals we have seen these valence electrons can be easily removed, isn't it? So the standard oxidation potential, it measures the tendency of an element to lose an electron from its valence shell. Okay, so standard oxidation potential means it gives the ability of an element to lose an electron from the valence shell. Okay, tendency of an element to lose an electron. Tendency of an element to lose an electron from its valence shell. That tendency, it is measured by the standard oxidation potential. That means from the standard oxidation potential values, we can know about the tendency of that particular element to lose an electron. Okay. So higher the standard oxidation potential, that means higher the standard oxidation potential, that means more the reducing power. Higher the standard oxidation potential means more the reducing power. So that is how it is measured. So down the group, the ionization energy decreases and the reducing properties increases. And also the tendency of an element to lose an electron, it is measured by the standard oxidation potential. That means it has got a definite EMF, the definite values will be there. And this higher the standard potential, oxidation potential, it gives the it means that the reducing power will be greater for that particular element. Okay. Next we can see some of the standard oxidation potential values of these alkali metals. Okay. See, alkali metals, lithium, sodium, potassium, rubidium, cesium. Okay. See, for lithium, the standard oxidation potential. This is the standard oxidation potential. For lithium, the value, it is 3.04. For sodium, it is 2.71. For potassium, it is 2.92. For rubidium, it is 2.99. And for cesium, it is 3.02. Okay. So here, which one has got the highest standard oxidation potential? Lithium has got the highest standard oxidation potential, while sodium, it has got the least standard oxidation potential. Lithium has got the highest standard oxidation potential, and sodium, it has got the least standard oxidation potential. So that means lithium, it has got the highest value, means lithium is the most powerful reducing agent, isn't it? Standard oxidation potential defines the reducing property of that particular element. So here lithium, it has got the highest value, that means it is the most powerful reducing agent. But the sodium, it is the least reducing agent since it has got the standard oxidation potential 2.71. Okay. But in actual practice, what happens is that this lithium, it will be giving off its electron most readily, isn't it? Lithium, it has got the smallest size, so it will be giving off, or it will be losing its electron most readily. So that is somewhat it has got some anomalous behavior between these two, lithium and sodium. So this anomalous behavior, it can be explained in terms of the ionization energy. Okay, so here we can see that this lithium has got the highest value. Since lithium, it is having the highest value, means lithium, it has got a smaller size, isn't it? So it has got, in the first shell it has got 2 electrons, and in the second shell it has got 1 electron, isn't it? That means this valence electron, it is closely or it is very tightly hold towards the nucleus, so that electron cannot be easily removed. So this that is the reason for the highest value of this standard oxidation potential. But the value of oxidation potential, see the value, it is very high, that means it can it has got the highest reducing property, that means it can easily remove the electron, isn't it? So both are having an anomalous nature, isn't it? While comparing the standard oxidation potential and also the size, we can say that some anomaly is there in the case of lithium. So that can be explained in terms of the ionization energy. So ionization energy means, what is ionization energy? It is the energy released when one electron or 1 or 2 electrons are removed from the valence shell, isn't it? How the ease to which an electron can be removed from the solid state or from the gaseous state. Okay. So we can define ionization energy as the property of an isolated atom, isn't it? Ionization energy, it is the property of an isolated atom, and how an electron can be removed, or how much energy is required to remove an electron, from the gaseous state, isn't it? So that property, it is called as the ionization energy. And normally for this alkali metals, it is univalent, that means it will be losing 1 electron. So a metal in the gaseous state, it will be losing 1 electron, so that it becomes univalent positive ion. Okay, so this is also in the gaseous state. So oxidation potential also, we can write the oxidation potential. Oxidation, so here simply ionization energy means, see here, it can remove 1 electron, isn't it? Only this much change that is given by the ionization energy, isn't it? The energy required for removing an electron from the isolated gaseous atom, that is called as the ionization energy. But in the case of oxidation potential, it is somewhat different from that of this ionization energy. In the case of oxidation state, it means that it is the overall change. Oxidation potential represents the overall change which is taking place in that particular species. That means we can write it as, see, suppose a metal which is in the solid state, it has to be converted to metal in the aqueous state, or it is ionized. From the solid state, it is ionized and 1 electron will be removed. So many processes are going on in between these steps, okay, in this reaction. So it has got several simpler steps also. This is the overall change for the oxidation potential, and in between there are so many steps involved. That is, here metal, it is in the solid state, and in the final state this metal is ionized and it is in the aqueous solution, and 1 electron is there. So this is the overall change, and this overall change, it is given by the oxidation potential. So this reaction, it will be taking place in further in further 3 steps. That means 3 steps are involved in between these conversion. Okay. And the 3 consecutive steps, involved in this change, that is, the first step is that, see here, in the first step, this metal, it is in the solid state, isn't it? So it has to be converted to the metal in the gaseous state, and it is ionized. Okay, so that is the first step. It will be losing 1 electron, and also it has to be converted to the gaseous state. Sorry, there is no plus charge. So here this metal, it has to be converted to the gaseous state. That is the first step. Then in the second step, this metal in the gaseous form, it has to be ionized. Okay, that means it will be ionized, it will be losing 1 electron to form M plus and 1 electron. Okay, so metal in the gaseous state, it is ionized, or it will be losing 1 electron to form M plus in the gaseous state. Then in the third step, this metal in the gaseous state, so here, see, it is converted to the aqueous solution, isn't it? So this metal in the gaseous state plus water. In water, it will be converted to M plus aqueous. Okay. So these 3 are the steps involved in this in the calculation of the standard oxidation potential. So the overall change gives the value for the oxidation potential. So the anomalous behavior is explained by these 3 steps. See, in the first step, we can see that this metal, it is in the solid state, it is converted to the gaseous state. What is the process for the conversion of solid to gaseous state? What is that process called? The process, it is called as the sublimation energy, isn't it? The process is called as the sublimation energy. So here, the energy involved, it is the sublimation energy. Then the next step, see here, metal in the gaseous state, it is ionized, isn't it? So it is 1 electron, it is removed from the gaseous state. So what is the energy involved there? For ionization, the energy required, or for the removal of 1 electron, the energy required, it is called as the ionization energy. The energy involved, it is the ionization energy. And see here, in the third step, the metal, it is combining with water, isn't it? Or it is going to the aqueous state, and so the energy, it is called as the hydration energy. The energy, it is called as the hydration energy. So here some energy will be liberated during this step, and this energy, it is called as the hydration energy. And so here we can say that for calculating the standard oxidation potential, the overall changes involved in these 3 energies, that is the sublimation energy, ionization energy, as well as the hydration energy, gives the net standard oxidation potential. Okay, so here in these 3 steps, we can say that, see here, hydration energy, it is involved in the last step. For lithium, it has got the smallest size, isn't it? So smallest sized ion means it will be having, what is the relation connecting small size and hydration? Smaller sized ion, it will be having the greater hydration power, or it has got the greatest hydration energy, isn't it? So lithium will be having the greatest hydration energy. And again, what happens is that it has got the greatest hydration energy. So in accordance, what happens, the standard oxidation potential value also increases, isn't it? So therefore we can say that this lithium, it has got a greater reducing power. It has got the greatest reducing power. See the value, it is about 3.04. So lithium, it has got the highest reducing property. So Li plus has got the greatest reducing property. The reason is that lithium, it has got the greatest hydration energy. So what happens, the value of standard oxidation potential also increases. So this is the anomaly present in between lithium and sodium. Okay. Even though lithium, it has got the smallest size, what happens, the hydration energy is maximum for lithium, and hence it has got the greatest reducing property. Hope you are clear with this. Then the next property, the 10th property, that is the lattice enthalpy. Lattice enthalpy. See here, lattice enthalpy. Lattice enthalpy means, the definition is that it is the energy released when a cation as well as an anion are brought together or brought close together to form an ionic solid. Okay, it is the lattice enthalpy. It is the energy released when a cation and an anion, when they are brought together in the gaseous state from infinity to form an ionic solid or an ionic crystal. Okay, that means, for example, when Na plus and Cl minus are brought together, when they are brought closer together to form an ionic crystal, that is, ionic crystal means it is NaCl. Okay, to form an ionic crystal, some energy will be released. That energy, it is called as the lattice enthalpy. Okay, I will be writing the definition. So lattice enthalpy, it is the energy released when the cations and anions in the gaseous state are brought from infinity to their respective crystal sites. To form 1 mole of the ionic crystal. So that is the definition for lattice enthalpy. And also here in this case, lattice enthalpy of alkali metals, this decreases down the group. Lattice enthalpy decreases down the group. Because the reason is that down the group, the alkali metals, the size of alkali metals is increasing down the group, and therefore the lattice enthalpy decreases down the group. Some lesser amount of energy will be required for bringing the positive and negative ions, or for bringing the cations or anions together to form a crystal. Therefore, lattice enthalpy decreases down the group. Okay, that is the 10th point. Then the 11th point, that is the flame coloration. Flame coloration, sometimes you had done the practicals in your plus one or plus 2, isn't it? That means sometimes if we are mixing a particular metal with concentrated HCl, we are making a paste with concentrated HCl and then in a watch glass, and then we are showing that mixture, that paste, then we are rubbing it with a glass rod, and after that we are showing this glass rod to a non-luminous flame, isn't it? And at that time this flame will be having some coloration, isn't it? Sometimes you have done your practical exam in your plus 2. That means we are making a paste of metal with concentrated HCl, and then it is shown to a non-luminous flame using a glass rod. That mixture, it is shown to a non-luminous flame using a glass rod. Then what happens is that there will be a color imparted to that non-luminous flame. So here this flame coloration, it is also an important property of this alkali metals. Okay, and so the alkali metals are lithium, sodium, potassium, rubidium, cesium. Okay, so these are the alkali metals. And for lithium, it will be this lithium when mixed with concentrated HCl, or when making paste with while making a paste with concentrated HCl and shown into the non-luminous flame, it will be showing crimson red. Sodium, it will be giving golden yellow to the flame. Then potassium will be giving pale violet. Rubidium will be giving reddish violet, and cesium will be giving sky blue. So these are the colors imparted by the different alkali metals to the non-luminous flame. Lithium crimson red, sodium golden yellow, potassium pale violet, rubidium reddish violet, and cesium sky blue. And also see here, the reason is that this alkali metals, they have got low ionization energies, isn't it? Low ionization energies are there, since the electrons, valence electrons, can be easily removed. And so what happens is that this, as a result of the low ionization energies, what happens? The electrons present in in these particular atoms, it will be excited from the ground state. So suppose if this is the ground state and this is the higher energy state, or this is the excited state. Okay. So what happens is that as a result of the lower ionization energies, it will be, the electrons will be moving from the, or the electrons will be excited to the next higher energy state. And also, since it has got a very low ionization energy, this excitation, this absorption of energy, it corresponds to the visible region of light. Okay. That means in the electromagnetic spectrum, so many radiations are there, and this absorption of energy will be taking place from the visible region of the electromagnetic spectrum. And as a result, see, visible region means it has got a color, isn't it? It will be having VIBGYOR. So from this visible region, the electrons will be absorbing energy, and after then it will be reaching to the excited state. After that, the electrons will be jumping back to the ground state. See, excited state, the electrons cannot stay as such. That means it is a highly unstable state. So in order to become stable, what happens? The electrons will be jumping back from the excited state to the ground state. So while returning back to the ground state, so here for moving to the excited state, it will be absorbing some amount of energy, isn't it? For moving to the excited state, it absorbs energy, reaches the excited state. Then it will be back to the ground state by releasing some amount of energy, or by emitting some amount of energy. So this emission, it will correspond to the visible region. Since absorption is taking place from the visible region, the emission, it is also from the visible region. So what happens is that this visible region means it will be having some color. So this emission corresponding to the visible region gives a color to that particular flame. Okay, so that is the reason for the flame coloration. And also this flame coloration, it depends upon this flame coloration depends on some properties also. The first one, that is the one of the factor favoring it is the density of the alkali metals. This alkali metals, it has got a bigger size, isn't it? Larger size is there, and hence what happens? Larger size means it will be having a lower density. Larger size means low density. Therefore, what happens is that lithium, it is the lightest metal, and also lithium is the lightest metal, and hence this lithium, it cannot be kept in kerosene or anything. This lithium, it is wrapped in paraffin wax. Lithium, it is kept in paraffin wax. So that is due to the low density. So this flame coloration, it depends on somewhat these properties also. Okay. So this flame coloration, it is important, you have to study. So then the next property, the 12th property, we can write it as the density. Larger size, this alkali metals has got a larger size, low density. Lithium, because of its low density, it is kept in paraffin wax. Sodium, as you know, it is kept in kerosene. Okay. Then the next property, that is the melting and boiling points. Melting and boiling points. See, this melting and boiling points are also very weak or very low. This alkali metals, they have got a very low melting and boiling point, since it has got a single valence electron, and also the melting and boiling point decreases down the group. Melting and boiling point decreases down the group. That is one point. Then the 14th point, that is the electronegativity. Electronegativity, as you know, these alkali metals, they are highly electropositive, isn't it? That means the electronegativity values are very low for this alkali metal since it is electropositive, isn't it? So the electronegativity values are very low, and also the electropositive character increases down the group and electronegativity decreases down the group. Just the reverse of electropositivity. Okay. So these are the properties of this alkali metals. Okay. Hope you are clear with this. This 14 points you have to study. Sometimes the some of the trending nature of this alkali metals will be asked. Sometimes how this coloration will flame color is imparted, color to the flame is imparted, so like that some questions will be asked in section B part. Okay, so you have to be very thorough with this portions, the characteristic properties of alkali metals. Okay, now we can go through the reactions, and also the reactions I will be taking in our next session. Okay, if you had got any doubt, please feel free to ask. Okay, so thank you and have a nice day.